So today we'll discuss the 11th session on relative velocity. In this session will be extremely important because we'll discuss the most important point of relative velocity, namely that is why displacement of a moving point in a given time interval depends on the frame of reference. So I'll mention it first. Okay. So 11th session. On relative velocity. So in 11th session on relative velocity, we'll discuss why displacement of a moving point in a given time interval depends on the frame of reference. So before discussing the 11th session, if anyone watches this video, you must first definitely go through the 7th video on relative velocity, in which the definition of reference frame has been given in very great detail and its meaning has been explained in a very great detail. So without reading the 7th video, going through the 7th video, you cannot understand this 11th video. So before reading the 11th video, you must definitely go through the 7th video. That is the basic definition of reference frame. Because this entire theory of this 11th session, that will depend on the knowledge of the definition of the exact knowledge of the reference frame. You should have a perfect understanding of the concept of reference frame, which has been fully explained in the 7th video. So only after reading the 7th video, after going through the 7th video, you should watch this 11th session. So today we'll discuss why displacement of a moving point in a given time interval depends on the frame of reference. Okay, first of all, we just formally define the concept of displacement. First, let us take the case of single frame. Okay. So suppose this is the frame F. This is the frame of observation from where we are observing a moving point. So first of all, we should note that whenever we measure the displacement of a moving point, it is in a particular time interval. That is, say, from time instant t1 to time instant t2. Whenever we measure the displacement of a moving point, it is in a particular time interval, say from time instant t barabar t1 to t barabar t2. Okay. Suppose we want to know the displacement of moving point with respect to some frame f in the time interval t1 to t2. If we want to know the displacement of point with respect to frame f in certain time interval, say t1 to t2, then we should see which location of frame f point p occupies at time instants t1 and t2. If we want to know the displacement of moving point p with respect to some other frame m in time interval t1 to t2, then we must first note down which locations of frame m does point p occupy at time instant t1 and t2. So suppose we want to know the displacement of a point p with respect to frame f in the time instant t1 to t2. So suppose at t barabar t1, point p occupies a location f1 of frame f at t barabar t1. f1 may be either a real location or imaginary location, as discussed on the 7th video. Before going through the 7th video, you cannot understand this 11th video. So I am repeatedly telling that you must first go through view the 7th video on relative velocity, in which the definition of reference frame has been given in exact great details. So if we are want to know the displacement of p with respect to frame f in t1 to t2, time instant t1 to time instant t2, then we should note which locations of frame f point p occupies at these two time instants. So suppose that time instant t barabar t1, point p occupies location f1 of frame f. f1 may be either be a real location of f or its extension or imaginary location. So now suppose point p moves and comes to some other location at t barabar t2. At t barabar t2, the same point p occupies location f2 of frame f at t barabar t2. So this location f1 which point p occupies at initial time instant t barabar t1, that will be called the initial location of point p. initial location of P with respect to F at t बराबर t1 and F2 will call at final location of P with respect to frame F. WRT meaning with respect to frame F at t बराबर t2. So this is F1 and F2. Okay. So F1 is the initial location of point P with respect to frame F at t बराबर t1 and F2 is the final location of P with respect to frame F at time instant t2. Okay. Achha, one more thing arises. While measuring the displacement, we should also specify from which frame we are drawing the diagram. That is one other aspect also. So in this case, we are observing the point P from frame F. We are observing point P from frame F, and at the same time, we are also going to draw the diagram from frame F. Okay, F1 is the initial location of P with respect to F at T1, and F2 is the final location of P with respect to F at T बराबर T2. So suppose we want to know the displacement of point P with respect to frame F in time instant T1 to time instant T2. So suppose, for example, we want to know the displacement of P with respect to F in say 9 a.m. to 10 a.m. So T1 becomes 9 a.m., T2 becomes 10 a.m. Now the point arises that at what time instant we are going to measure the displacement. At what time instant we are going to calculate the displacement of P with respect to F. So that calculation will be done at 10 a.m. Suppose we want to know the displacement of P with respect to F from 8:30 a.m. to 8:45 a.m. So we'll calculate the actual displacement at 8:45 a.m. Suppose we want to know the displacement of P with respect to F say from 7 a.m. to 8:30 a.m. Then we'll calculate this displacement at 8:30 a.m. Not before that or not after that. Because unless and until the motion is completed, we cannot calculate the displacement. So motion has first to be completed. Motion, suppose we are measuring the displacement from T1 to T2, then motion will be completed only at T2. So only at T2 only we will calculate the displacement of P with respect to F in the time interval T1 to T2. So I am repeatedly telling it, alright. So now see, we want to know the displacement of P with respect to F in the time interval T1 to T2. As mentioned just now, we will calculate the actual displacement of P with respect to F at t बराबर t2. So at t बराबर t2, P occupies the final location F2 of frame F. Now we should know at t बराबर t2, where is the initial location of F1 of frame F of point P at t बराबर t2. Now we are drawing the diagram from frame F. With respect to frame F, F is fixed. And as discussed in the 7th video on relative velocity, F1 is rigidly connected to F. So if F is fixed, then F1 is also fixed because it is rigidly connected. It cannot move. So this means at t बराबर t2, F1 will be at same location as it was seen at t बराबर t1. At t बराबर t1, F1 was at this location. So at t बराबर t2 also, F1 will be at this location. And at t बराबर t2, F2 is at this location. So displacement of P with respect to F in the time interval T1 to T2 will be this arrow from initial location F1 to final location F2. So this is the displacement of P with respect to F in the time interval T1 to T2, dPF. D meaning displacement, P meaning point, and F meaning the frame with respect to which the displacement is being found out. Okay, alright. So this is the displacement. So I'll summarize one of the main important points. If we want to know the displacement of P with respect to F in T1 to T2, then for that we should see the locations of F which P occupies at these two time instants. If we want to know the displacement of P with respect to M in T1 to T2, then we should note down the locations of M which point P occupies in T1 to T2. Second, initial location and final location concept I have discussed. For example, in this case, F1 was the initial location of P of frame F, and F2 is the final location of P of frame F at T2. And if we want to know the displacement of P with respect to F in T1 to T2, then we should note actually calculate the displacement at T बराबर T2. Okay, fine. So this much I have said. I hope it is clear. So I am rubbing it. All right. So now suppose we are given two frames M and F. We have to understand only one thing. Why displacement of P with respect to F with respect to M in a given time interval will not be the same in general. This only we have to understand. So see, suppose that this is the frame F. This is the frame F, okay. This is the frame M. This is frame F, this is the frame M. Suppose M is in motion with respect to F. M moves with respect to F. Now M can move with respect to F in several ways, as discussed in previous videos on relative velocity translation rotation chapter. In the previous videos you will get it if you refer to the previous videos of this relative velocity chapter. So let us take the simplest case, that M undergoes rectilinear translation with respect to F. Suppose M moves in a straight line with respect to F, say along rightward direction. So this arrow indicates the motion direction of M with respect to F. Okay. This indicates the motion direction of M with respect to F. Rectilinear translation, we have assumed, simplest case. So now see, this is point P. This P is a moving point which is being observed simultaneously from the two frames M and F. Suppose we want to know the displacement of P with respect to F and with respect to M in the time interval T1 to T2. We want to know the displacement of P with respect to F and with respect to M in the time interval T1 to T2. From initial time instant T1 to final time instant T2. Okay. So now see. This is the location of P at time T barabar T1. At T barabar T1, point P occupies location F1 of frame F and location M1 of frame M. At T barabar T1, point P occupies location F1 of frame F and location M1 of frame M. This is at T barabar T1. Okay. Now what happens? This point begins to move. Okay. Let us assume, so this is the situation at T barabar T1. Alright. Fine. Now see what happens. I'll just make it a bit smaller, because then this space will be, I'll write it here, okay. At T barabar T1, point P occupies location F1 of frame M, F, and location M1 of frame M. This is at T barabar T1. So now, what happens? P also moves with respect to both these frames, M and F. Now what happens, suppose at T barabar T2, point P comes here, suppose. This is given, okay. So at T barabar T2, point P occupies location F2 of frame F and location M2 of frame M. This is at T barabar T2 and this is at T barabar T1. Okay. So at T barabar T1, point P occupies location F1 of frame F and location M1 of frame M. And at T barabar T2, point P occupies location F2 of frame F and location M2 of frame M. Now we have to determine two things. First, we have to find the displacement of P with respect to F in T1 to T2. And second, we have to find the displacement of P with respect to M in T1 to T2. Fine. So first of all, what we will do, we will find the displacement of P with respect to F in T1 to T2. So one more thing, we are going to draw the diagram from frame F itself. Okay. So see, we want to know the displacement of P with respect to F in T1 to T2. For that, we must note down which locations of frame F point P occupies at these two time instants. So at T1, point P occupies location F1 of frame F. That will be called the initial location of P with respect to F, as discussed previously just now also. This is the initial location. Initial location of P with respect to F. That is at T barabar T1. That is the initial location. Also at T barabar T2, point P occupies location F2 of frame F. So F2 is the final location of P with respect to F. That is at T barabar T2. Final location. Now displacement is being measured in the time interval t1 to t2. As stated just now, this displacement will be calculated at t barabar t2. So at t barabar t2 we have to note down where f2 will appear to be and where f1 will appear to be. At t barabar t2, f2 is at this location. Now diagram is being drawn from f. With respect to f itself, f is at rest. f1 is rigidly connected to f. So if f is at rest, f1 which is rigidly connected to f, that is also at rest. So at t barabar t2, f1 will appear to be in same location as it was at t barabar t1. At t barabar t1, f1 was here. So at t barabar t2 also, f1 will be at same location. And at t barabar t2, f2 is here. So displacement of p with respect to f in t1 to t2 will be the vector from initial location f1 to final location f2 as calculated at t barabar t2. So this is the displacement of p with respect to f in the time interval t1 to t2, dpf. So dpf is the displacement of point p with respect to f in the time interval t1 to t2. Fine. So this is the displacement. Displacement is from initial location to final location. And that displacement vector will draw at t barabar t2 as stated just now. So displacement of p with respect to f in t1 to t2 has been shown here. Is it alright? Fine. Now see, we have to know the displacement of p with respect to m in the time interval t1 to t2. We have to know the displacement of p with respect to m in the time interval t1 to t2. This we have to know. For that we have to consider which locations of frame m point p occupies at these two time instants. So t barabar t1 point p occupies location m1 of frame m. So m1 will be called the initial location of p with respect to m at t barabar t1. And m2 will be called the final location of p with respect to m at t barabar t2. Fine. So now we are drawing the diagram from, actually we are finding the displacement in t1 to t2 with respect to m. So actual displacement calculation will be done at time instant t barabar t2. So we should note at t barabar t2 where m2 and m1 will appear to be. At t barabar t2, m2 is here. Now we should know at t barabar t2 where m1 will appear to be. Now diagram is being drawn from f. With respect to f, m moves rectilinearly in rightward direction. Now m1 is a location of m, that is, it is rigidly connected to m. This means that if m moves rightward, m1 will also move, m1 location m1 of m will also move along with m to the right. So at t barabar t2, m1 will somewhere appear to be here somewhere at t barabar t2. At t barabar t2, m1 will appear to be at this location. And at t barabar t2, m2 will appear to be at this location. So displacement of p with respect to m in t1 to t2 as calculated at time t2 will be from initial location m1 to final location m2. So this is the displacement of p with respect to m in the time interval t1 to t2. Now you can see that these two arrows are not the same. This is dpf, this is the dpn. These two vectors are not the same because they have different directions, they have different magnitudes. So displacement of p with respect to m in t1 to t2, that is dpm, and displacement of p with respect to f in t1 to t2, that is dpf, are not the same. They are different. Okay? Now why are they different? This is because displacement is from initial location to final location. So in displacement is being found in the time interval t1 to t2, and this will be calculated at t barabar t2. So at t2, final location of p in both the frames f and m, that is f2 and m2, they are coincident. And at t barabar t2, initial location of p in both the frames f and m, that is f1 and f2 and m1, they are non-coincident. T barabar t2, m1 and f1 are non-coincident, and at t barabar t2, f2 and m2 are both coincident. Displacement is from initial location to final location. So with respect to m, displacement is from initial m1 to final m2 here, this arrow. And displacement of p with respect to f is from f1 to f2 here, this arrow. So f1 and m1 are non-coincident at t barabar t2, and F2 and M2 are coincident at T barabar T2. So since final locations of P in both the frames are coincident at T barabar T2 and initial locations of P in both the frames are non-coincident at T barabar T2, therefore displacement of P with respect to these two frames in a given time interval T1 to T2 is not the same. Because, so we'll say, so what is the basic idea? Why is it that displacement depends on the choice of frame in the time interval T1 to T2? Because M moves with respect to F, therefore at T barabar T2, final locations of P in both the frames are coincident, and because M moves with respect to F, therefore at T barabar T2, initial locations of P in both the frames F and M, that is F1 and M1, are non-coincident. So displacement from in M frame will be initial to final, M1 to M2, and displacement of P in F will be from F1 to F2. So final locations in both the frames are coincident and initial locations of P in both the frames are non-coincident. So displacement of P in both the different frames will not be the same. This is the basic idea of relative velocity. Okay. So why displacement depends on the choice of frame? I am repeatedly telling it. Because at T barabar T2, final location of P in both the frames, that is F2 and M2, are coincident. And at T barabar T2, initial location of P in F and M, F1 and M1, they are non-coincident. And displacement is from initial location to final location as seen at time T barabar T2. So, initial location of at T barabar T2 of M is here. Initial location of P in F frame is here. They are non-coincident, they are at different locations. And final location of P in both the frames, they are at same location. Displacement is from initial location to final location. Final location, both the locations are coincident. Initial locations are non-coincident. So in one frame, displacement will be from here to here. In other frame, displacement will be from here to here. So these two displacements are not the same. So these two displacements are different. So this is all. So this is all the basic idea of relative velocity. Okay. So how do we write down the exact reason? So we'll summarize it in this way. Displacement is from initial location to final location. If we want to know the displacement in T1 to T2, we'll calculate the actual displacement at T barabar T2. At T barabar T2, final locations of P in both the frames M and F are coincident. And because M moves with respect to F, therefore at T barabar T2, initial locations of P in frames F and M, that is F1 and M1, are non-coincident. Displacement is from initial location to final location at seen at T2. So displacements in both the frames are different. Fine. So at T barabar T2, final location, this is a summarization. Fine. At T barabar T2, final location of P with respect to M and F are coincident. Final location of P with respect to M and F are coincident. This I'll rub it, okay. Final location of P with respect to M and F are coincident, and initial location P with respect to M and F non-coincident. Why are they non-coincident? Because M moves with respect to F. That is why. Because M moves with respect to F. So initial location of P with respect to M and F are non-coincident, and final locations are coincident. Displacement is from initial location to final location. Final locations at same location. Initial locations are at different locations. So in one frame displacement is this, in another frame displacement is this. So displacement is dependent on the frame of observation. Fine. This is all about the basic theory of relative velocity. So you can see the importance which the definition of reference frame plays here. If you don't know the definition of detailed definition of reference frame as given in the 7th video, then this cannot be understood. So I am repeatedly telling that whenever you watch this 11th video, you should definitely watch the 7th video and then continue watching this 11th video. Otherwise, without knowing the exact definition of reference frame, you cannot understand the basic theory of relative velocity. So displacement depends on the frame of reference. Actually, one more thing. This displacement we found in the frame, two frames M and F, in the time interval T1 to T2. That is in some finite time interval, say from 9 AM to say 9:30 AM. If displacement is different in two frames in a finite time interval, then by the same argument, displacement of P in two frames in an infinitesimally small time interval, that will also be different. If displacement of P in a time interval is different in two frames, and this statement should be valid irrespective of whether the time interval in which the displacement is being found, is it finite or is it infinitesimally small. In both the cases, displacement will depend on the frame of reference. So in T to T plus dt also, displacement of P in both the frames will be different. So displacement of P with respect to frame M will be drm, and in the time interval T to T plus dt. And displacement of P with respect to F in T to T plus dt will be it is F. So these two displacements are not the same. So drf is not equal to drm by the same argument which we discussed here. Difference that in this we took a finite time interval, but here we are taking an infinitesimally small time interval. But the same theory applies here also. So T to T plus dt, displacement of P with respect to F is drf, and displacement of P with respect to M is drm. By the theory which we discussed just now here, drf and drm are not equal. And if we divide these two by dt, length of the time interval, then we get the velocity. So what do we get here? I'll rub it, okay? So drf is not equal to drm. So drf by dt is also not equal to drm by dt. But drf by dt is nothing but the velocity of P with respect to F at time t. And drm by dt is just the velocity of P with respect to frame M at time instant in t. These two are not different. They are different. They are not the same. They are different. So velocity also depends on the frame of reference. Because displacement depends on the frame of reference, velocity also depends on the frame of reference. Achha, what about acceleration? Acceleration is nothing but the change in velocity in unit time, dv by dt. Since vpf and vpm are not the same, therefore dvpf by dt and dvpm by dt, they are also not the same. But dvpf by dt is nothing but apf, and dvpm by dt is just equal to apm. These two are not the same. So accelerations of the point P in two frames M and F are also not the same. So acceleration also depends on the frame of reference. Velocity also depends on the frame of reference. Displacement also depends on the frame of reference. Fine. This I'll grab, okay? So one more thing. Trajectory. When we talk of trajectory of a moving point, meaning path which the point P follows in a given frame. Suppose in a particular frame point P moves in a circle, then we say its trajectory is circle in that frame. Suppose a point P moves in a projectile, parabolic path, we say its path is a parabolic path. That is the trajectory of path. So trajectory of a moving point is decided by its velocity. Since velocity depends on the frame of reference, therefore trajectory of a moving point also depends on the frame of reference. Fine. So this is all about the basic theory of relative velocity. This is all about the basic theory of relative velocity. So today we found that because displacement depends on the frame of reference, so velocity depends on the frame of reference, acceleration depends on the frame of reference, and trajectory of a moving point also depends on the frame of reference. So I hope it is clear to you. Okay. So this 11th session was, we can say it was a summary of the chapter on relative velocity. This is all about the basic theory of relative velocity. Whatever follows next is just the calculation. It is nothing but the just calculation, nothing else. It is just the calculation of the basic concepts. Okay. So today, 11th session, I have talked of this much. In the 12th session, we'll take up some more examples to demonstrate this concept. In the 12th session, we'll take up some more definitions, some more examples to clear this concept, to strengthen this entire concept of relative velocity. It becomes fully internalized. So for that, we'll take up some more examples to show why displacement depends on the frame of reference, so that this concept becomes absolutely clear. I hope it is all right. Okay. So let's close it here. Okay. Fine.